As you sit here watching this video, you are being bombarded by air molecules. Not scared? I mean, yes, sure, an air molecule is pretty small, but these air molecules that hit you are travelling at about 1,800 metres per second, which is faster than a rifle bullet. That doesn't mean they go 1.8 kilometres in a second. In practice, they only get about 10 to the minus 9 of a metre before banging into something else. But nonetheless, when they hit your skin, that's the speed they're travelling at. And the number hitting your skin in a second is colossal, about 10 to the 27 air molecules hitting you every second. So between now and now, you've been hit by 10 to the 27 air molecules travelling faster than bullets. And the total effect of all this constant bombardment is a force, a very strong force. If you're at sea level on Earth, the typical combined force of all these molecular impacts is about 100,000 newtons for every square metre. So that basically means the outside of your skin is being applied to the same force as if a 5 Indian elephants sat on it, about 10 tonnes worth of force. So it's absolutely enormous. This force is called air pressure, and it is very, very big. Why aren't we all squashed totally flat by this immense pressure? Well, luckily there's an exquisite balance. Sure, my skin is being hit by this colossal, enormous force from outside, but then also the blood inside is applying the same pressure back out. The air inside my lungs is pushing outwards at the same pressure as the air outside my lungs is pushing inwards. So it's a bit like being out of a small country in the middle of a superpower battle. You've got this immense force one side, immense force the other side, but they're so beautifully balanced that normally you can go around your life without even worrying about air pressure. If for some reason the right-hand side of my body had no air pressure, it was in a vacuum, then I would be flung sideways at some enormous rate by the huge air pressure. There are a few situations where you can see this. One example would be something like a pack of chips. If it's manufactured in Sydney, the bag might be quite loose there, but by the time it comes up to Canberra, where air pressure is about 8% less, it can be quite tight and expanded. A very common example is scuba diving. Let's imagine you've got your air tank which is feeding you air and you dive underwater. As you go deeper underwater, pressure increases really fast because water is very dense. In fact, 10 metres down under the sea, pressure is about double atmospheric pressure, so it's an extra 100,000 newtons per square metre. If you tried to breathe in, the regulator, the face mask, supplies you with air at the local pressure. If it's supplied with anything else, your lungs would be crushed. So you're breathing in air when you're say you're 30 metres down at 4 times atmospheric pressure. Normally that's not a problem as long as you breathe in and out. The regulator supplies you air at the same pressure as what's around you, otherwise you wouldn't have strong enough muscles in your lungs to be able to suck it in. The trouble comes if when you're deep underwater you panic, hold your breath and run for the surface, swim for the surface. Don't do this. If you do, the air inside your lungs will be at the pressure of the last breath you took, which might be 4 times atmospheric pressure if you were 30 metres down. As you go up, that air will start expanding as the pressure outside gets less and less. And you won't notice this because you don't have inside your lungs nerves. And in fact, it can rip you apart. So one of the first things you're taught when scuba diving is, whenever going up, keep breathing. As long as you're breathing, just a gentle little flow of air in or out, and that keeps the pressure inside your lungs and outside balanced. So, anyway, air pressure, very strong force. Measured in pascals, a pascal is a newton per square metre, so it's telling you how much force there is per square metre. As I said, it's typically hundreds of thousands, so very, very high for most practical applications. The equation for the pressure exerted by a gas is the ideal gas law, which tells you the pressure times the volume is equal to the number of atoms N per unit volume times the Stefan-Boltzmann constant K times the temperature, also sometimes called MRK if you use moles rather than the number of atoms. And that tells you that for an ideal gas, if you squish it, the pressure goes up, and if you increase the temperature, the pressure goes up. So the pressure basically depends on the temperature and the density.